Hey everyone, Shiva here. Today we're diving into the world of semiconductors. These tiny chips power everything. From your phone to your gaming PC, it's all thanks to these marvels of engineering. But have you ever wondered how they're made? What does it even mean when a chip is 7 nanometers or 5 nanometers? Let's break it down. The NM stands for nanometers. A nanometer is 1/1000th of a meter. That's incredibly small. To put it in perspective, a human hair is about 75,000 nanometers wide. In the world of semiconductors, the technology node, often referred to as just node, refers to the size of the transistors on a chip. Transistors are like tiny gates that control the flow of electricity. The smaller the transistors, the more you can fit on a chip. This means more processing power and better energy efficiency. So, when a company announces a new chip with a smaller node, like going from 7 nanometers to 5 nanometers, it's a big deal. It's like cramming even more transistors into the same space, making our devices faster and more powerful. For decades, the semiconductor industry has been driven by Moore's law. This observation, made by Intel co-founder Gordon Moore in 1965, states that the number of transistors on a chip doubles approximately every 2 years. This prediction has held remarkably true. It has fueled incredible innovation in computing power. The drive to shrink transistors is relentless. Each new node brings significant advancements. A 90-nanometer chip, common in the early 2000s, was a marvel of its time. But it pales in comparison to today's 5-nanometer chips. The transition from 90 nanometers to 7 nanometers was a major leap forward. It brought about significant performance improvements and power reductions. This paved the way for the powerful mobile devices and laptops we use today. The move to 5 nanometers was even more impressive. It further pushed the boundaries of what's possible. This node enabled the creation of incredibly powerful and efficient chips. These chips are found in the latest smartphones, artificial intelligence applications, and high-performance computing. The relentless pursuit of smaller nodes brings about a trifecta of benefits: increased performance, reduced power consumption, and higher transistor density. Smaller transistors mean electrons have to travel shorter distances. This results in faster switching speeds and overall performance improvements. Think of it like this. A smaller racetrack means faster lap times. Smaller transistors also consume less power. This is crucial for mobile devices where battery life is paramount. With lower power consumption, devices can run cooler and longer. Finally, smaller transistors allow for higher transistor density. More transistors on a chip mean more processing power. This translates to more complex calculations, faster data processing, and overall smoother user experiences. Section 4. Challenges at the nanoscale. Heat, leaks, and quantum tunneling. Shrinking transistors to such incredibly small sizes is not without its challenges. As we delve deeper into the nanometer scale, we encounter obstacles that require innovative solutions. One major challenge is heat dissipation. Packing billions of transistors into a tiny space generates a significant amount of heat. Managing this heat is crucial to prevent performance degradation and ensure chip reliability. Another challenge is current leakage. As transistors get smaller, it becomes harder to control the flow of electrons. This leakage can lead to power loss and reduced battery life. At these incredibly small scales, quantum effects like quantum tunneling come into play. This phenomenon, where electrons can pass through barriers that would normally block them, can disrupt transistor operation. Section 5. The future of transistors, 3D architectures, and beyond. The future of semiconductor technology lies in pushing the boundaries of innovation. While traditional scaling methods are reaching their limits, researchers and engineers are exploring new frontiers in transistor design and manufacturing. One promising avenue is 3D stacking. This involves stacking multiple layers of transistors on top of each other, interconnected vertically. 3D stacking offers a way to increase transistor density without shrinking the individual transistors any further. Another area of exploration is new materials. Traditional silicon-based transistors are approaching their physical limits. Researchers are investigating materials with better electrical properties, such as graphene and carbon nanotubes. The quest for sub-2 nanometer nodes continues. These nodes represent uncharted territory in the world of semiconductors. They hold the promise of even faster, more powerful, and energy-efficient devices. The world of semiconductor technology is constantly evolving. As we push the limits of what's possible, one thing remains certain. The future holds exciting advancements that will continue to shape the technological landscape.